Hi, welcome to Autobit 2T. I'm Dave, and today we're going to be trying to increase the power by doing some flow testing on the exhaust duct of my Kawasaki AR93. We're going to do some modifications with some modelling clay, see if we can increase the flow that we're going to measure using the TalkSoft software. Why am I doing this? Well, I guess most of you are probably aware of a guy called Thiel. In his book, The Two-Stroke Master, that I've been reading, there is a bit to note. I asked for a flow meter to check the effectiveness of changes to the cylinder ports. Thiel used flow meters, mine's slightly different setup, however it's measuring airflow. I believe it is something that could help us develop more power. Along with seeing that in Thiel's book, I've also had some conversations with a guy called Bill Schiff on some flow visualization I put up. So a bit of a conversation on that sowed the seed, as well as looking for somehow to flow test a two-stroke engine. Other resources as well, there's a British guy who lives in America called David Vizard. He's got a lot of videos on the internet on his YouTube channel, particularly flow testing stuff. I intend to do the exhaust today. Transfers will be a later video, and then following on from that, I want to actually physically modify the cylinder so I can try some inserts, so I can measure flow from 3D printed inserts, and then use my CNC machine that I need to get going to then make a CNC insert for the exhaust duct that I've tested in 3D printed form, and see actually how that works on the dyno. If you're interested in that and how we get on in the future as we continue to evolve this project, then hit that subscribe, hit the notification so you'll see when I continue to upload. Hopefully I'll get a few more videos out over Christmas as well, now I've got a little bit more time. Yeah, and we're nearly up to 4,000 subs, so thank you for everyone who's recently subscribed. Brilliant. A lot further on than what I thought it would be, so thank you. Just wanted a quick look at the exhaust duct port. So you've obviously got a piston that can be all the way, obviously closing the port totally, and at any position in between. So I'll just notionally put a piston in there. And as you can see, this duct has to cater with lots of different positions. It's got the flow going into it initially only a small area, and this flow's coming in, and it's obviously got a big void here, and then as it gets further down, when it goes down to the bottom, I imagine it's probably a bit more uniform flow. And for what I'm seeing at these not fully open positions, there seems to be quite a lot of slack flow there, and I'm getting a cotton attaching to the face of the piston. So really the blowdown's key, so if we can kind of optimize the flow at the blowdown to get the most amount of gas out, it should assist us. Other issues as well, obviously we have all the exhaust gases going out of the duct, but also with a two-stroke going back the other way, when the stuffing pulse comes in, we've got some fresh charge that we want to go back in. So I'm only doing flow testing going this way, but I've got to bear in mind that there's also flow going back in when it gets reversed. So we're kind of optimizing it for flow out. How that's going to affect flow back in, I don't know. So say we want to optimize this duct so it flows a little bit better. At sort of blow down areas, I'd imagine, and there's a lot of talk about filling the port floor. At the minute this piston comes down to here. However, there's not a lot of flow going on there. So there's potential for filling this floor, and I guess to actually smooth it out. And it's all about keeping this volume of this duct as small as possible so you don't dissipate energy into it, but also keeping the cross-sectional area. If you look at this way, and if you've got a small duct versus a big duct, and if we put this section here, say if you've got all the burnt gases on this side, and then you've got the fresh charge coming out like that, the bigger area you've got, the more this can mix. And obviously this is in a perfect world, it's not going to be like this, it's going to be chaotic. However, it's all about minimising this area so there's less interface between the burnt exhaust gases and the fresh charge, particularly when it goes back in, because if these are mixing heavily, you're going to get burnt gases back into the cylinder. So I believe definitely want to get the flow out, but there's also a certain element of how much fresh gas we get back in, where it's aimed, and probably the tumble and swirl that we put into it, which again helps with the combustion, speeds things up and makes more power on the next stroke. I bought this flow venturi, so that gets connected to the pipe. You can just see it here. These are the instructions. So pipe comes out, 300mm pipe into this venturi. Got some brass nipples that I'm going to put in, and they sit in there in these 3 ports. I've got to ensure that I don't bottom them out on that hole either. I'm going to test the pressure with these manometers. So you can see I've just got the same one. You're measuring the pressure, so you've got a reference pressure. I've got 2 of these, so one can sit there, reference pressure. The other one's going to measure the delta. So as well as exhaust ducts, it will do transfers as well. The piston's in there and it's moved at different points, and the pressure drops obviously inputted into the program, and then it works out your time flow area. I'm not too bothered about transfers at the minute. I want to test this exhaust port. Apparently you can put plasticine in there. I've got a few ideas of how I'm going to try different ducts. I'm interested in, can I get more power out of this just by altering this duct. This is 32mm internal diameter, and it's about 36. Now I'm lucky it just fits a really tight fit on my stub. I get it in square. So that's going to go obviously in there. That'll be bolted in. That'll sit on there. That's the connection. The next end needs to go into here. I've got a bit of masking tape because it makes it a real good fit. On the other end, I then need to connect the other end of this pipe. So to do that, I've got one of these couplers, which I shall use. Another bit of pipe in there. And then my hoover. This is the end of my hoover. I've got one of these. That fits really nice. It's quite a tight fit. I can't get this tube into here, so I'm going to have to probably break this open. But I think it will fit in there. Quite a snug fit. So that's the plan. This is my shop vac. It's a Miele. I don't know how you pronounce it. In the instructions, the guy, Anthony, was saying to put holes in a pipe and then use a sleeve to meter it. I've got 6 power settings on this, so I can vary. I think I should be able to vary it to get the pressure right. I can alter the bleed here as well, so I'm hoping I can control it to set the pressure right just with this and with the power settings. If not, I do have the bigger bit of pipe, and I'll just have to drill some holes and make this slide over it to meet the flow a bit more. I don't want that going in here and bulging out in there because it will affect the readings. So I'm going to put a little washer on here. I don't think it's going to hit it anyway because it's only going to come to there, and that hole's a bit further. But just to make sure, I'm going to put one of these washers on, and these should just self-tap anyway. I have to get a little spanner on that now. Yep, that seems okay. It's the brass inserts in, and I haven't impacted down there. A PVC bit of pipe, so I've been recommended distance from where it connects to the exhaust port 10 times the internal diameter. So this is 32mm, so that's 300. Doing a 20. So this is the tube, and it's a real tight fit, so I've just got to connect that to this now. See what that's like. I'd say one more. What's that like? Oh, that's nice. That's a good fit. Like that. That's in. There. Good fits there. Just it goes into the hoover. Finally, I just need to bolt this on. I'm going to put a little bit of sealant on there as well, so I get a good seal on this face. So, to do the exhaust flow tests, you need to block up the transfer ports. So obviously there's no rogue air coming from there. I was going to tape it, but I just did some vinyl mould. Just chop the top off, just push that in. I think that's going to plug it fairly well. Not a lot there, going to get through there. Taped over that where it feeds into the crankcase, and I've just made a bung out of that black stuff just to fit in there to block the intake. So for the testing, you start off with about 1.5 mil of the port uncovered. I've gone for, well, between 1 mil and 1.5 mil. I've gone for 21 mil because that's what works. I've got, if I switch this on, this depth gauge. Luckily, it goes just below 0, and it's about the distance, the difference in the distance from there to the top of the piston ring that's actually controlling the port, because of the Dykes ring, is that distance. So when I set this to 21 mil, and then I rest this on here, and then if I push down, keeping it square, and if I just move like that, because obviously that's lower, so as long as I go over the high point, I know we're at 21 mil. And then as I go, I take a reading every 2 mil. There we go. 23. I'll lock that off and then do it again. Instrumentation. Got these 2 manometers. I've got this one, which is the pressure at the entry into the Venturi. I guess that's the reference pressure it's using. You're using you can see it, centimeters of water. The second one is measuring differential pressure, so it's measuring the pressure at the Venturi throat and obviously at the inlet. I enter this into the program along with the temperature and also the piston position, and is what it does, it works out the flow time area, which is pretty much specific time area figures you'd use for port areas, but it's also factoring in the flow capability of the exhaust duct. And obviously in another episode when I look at the transfers, it will factor that in. It goes down to my hoover. First time I do it, I have to have it on the hearing setting, which is less vacuum, and I do have to exit some of the flow from there, otherwise I max out this gauge. And then as I go, once I get down to about the 3rd reading, I've got it maxed out and I've got this done, and then the pressure here does drop because it can't sustain that high pressure, but the software figures all that out. First position 21 mil, switched on, ready for data collection, test 1, and then I'll do subsequent tests. I've already done a load of testing just to try and get consistency, to see if it does, if I can, and I'm quite happy with the procedure I've got. First test, we're down at ear sign because it's too much, because we've only got very small gap. So you'll notice as I switch on the hoover, this will come up, and 140 then it will max out, so I'll be adjusting it with this.
Hey, welcome to the TalkSoft website. This is where the software is that I use. On here, there's a vast array of different programs. You can actually, the standard time area, there's exhaust, calculations, there's squish design, redesign, lots and lots and lots of different things, lots of different packages. However, I went for the transfer time flow area and exhaust time flow area. Membership, it was £25, which I think is peanuts. It's really good. So if I take you on there, and then that opens up this web page, and you can go through. That's the exhaust time flow area program, and it calculates the potential power capability of the engine. Time areas calculate traditional method using exhaust port actual dimensions. It's fantastic cool, as it says, but however, if it doesn't flow as well as the time area calculated from the port area says, then your engine isn't going to perform as well. So by using this, you can actually see how much flow the not only the port but the duct as well can handle, and give you a more accurate power prediction. That's the flow control Venturi, and you order that. It gets 3D printed, sent to you. It's about 80 euros, I believe. And then yeah, there's a few test cases that he's done. So that's that. So for me, I've put in all the data, engine dimensions, to speed up what I want it done. That's your deck height. That's the diameter of the outlet. So it's 30mm at my stub. That's the distance to the port opening from the top of the cylinder. 19.5 I've used, that's to the ring just opening the port. 31.9 is for the transfers. Pressure of the day, and these are the Venturi dimensions. So inlet 32mm internal diameter of the tube. The orifice itself is 20mm at the throat, and that's the length of the extension I put on. So then you just go in and enter your data. First data collection point is at 21mm, which is 1.5mm open of the exhaust port, just for easy numbers for me. And then I did a step every 2mm. Putting the temperature did vary a little bit throughout the tests. Starting off with the high pressure, that's about 2 psi, and obviously as it opened, the vacuum couldn't sustain the high pressure. However, this is the beauty of this program, it just calculates it for you. So you put your data in, hit calculate, and that gives you, and this is the standard exhaust that we're going to look at in a bit, the standard exhaust port. So it said it should give 21.5 horsepower for the exhaust area, or 26.6 actual blowdown. So, but that is importantly at the crank. So this is power at the crank. So probably 15 to 20% losses. What we're at that, if you call it 20%, you're at 21. So in theory, something else in my engine's holding me back. So it might not be the exhaust duct. It could be the transfers.
Okay, just going to talk through the results. So I did 4 tests. I did test 1, which was standard. Test 2, I put like a little lump in the middle. Test 3, I actually filled that in and made it flatter. And then test 4, I put another lump on top of the flatness. So what results did we get? So I was going to write them out. So test 1, that was standard. And the exhaust power output, so for the exhaust it was 25.5 and blowdown 26.6. Then test 2, on the bottom of the exhaust duct I made like a little vein in the middle, and that gave me 26.8 sort of horsepower for the exhaust and 27.6 for the blowdown. So quite an improvement just from putting that little vein in there. Third test, I then filled it in, so test 3, I sort of took this bit and then I filled it in, so it's almost like a flat bottom. That didn't actually make much difference. actually dropped a little bit on the exhaust power and about the same on the blowdown. I did do a previous test of this and I did get a slightly better result than that, so I don't know if it's just the way I put the modelling clay in. However, it seems to like this little bit of a revision in the middle, that rise. So for test 4 I tried a bit more of that, so it's basically what I'd got, and then I put a little another lump on there like that, and that did get me an increase again. So we went to 26.9 for the exhaust and 27.9 for the blowdown in terms of the power. So as you can see, from standard, exhaust potential has gone up by 1.4, and for blowdown again that's 1.3, which says to me we should be able to get a little bit more power if I optimise the exhaust duct. That said, this is saying I can get quite good power from the exhaust. I may need to look for restrictions elsewhere, which is when we're going to come on to look at the transfer flow after that.